Hello and welcome to this new video. In this video, I will do a very quick overview of the possibilities of Python, just to get started. Now, as you know, Python there are several text editors for Python, but I chose the Jupyter Notebook, which open in your browser, because it's very interactive, as you shall see. Okay. So I first wrote down some very useful shortcuts that I hope you will try by yourself. And the first thing I will start with is the basics. I will start with the basics: the print command, the loops, the functions, the math module, the numpy module, and basic plots. Okay, so the first thing one learns in a new language is to print hello world, okay, as you know. So the syntax is very simple: print between parentheses, and you type the text you want to print between quotes, okay? Now, this is actually Python 3.6. The syntax for Python 2.7 was a little bit different. It didn't need parentheses, okay? But now we shall use Python 3.6 or 3.7, I think now. So if you want to run this cell, you have two options. Either you can click the run button here, or you just type Shift Enter, okay? So as expected, it works. Now, suppose you want to print the same message 10 times, okay, with the index each time. Let us see what happens. So we have a very simple for loop, as in other languages, but no two things actually. There are no brackets in Python. Rather, Python relies on indentation. So pay attention to two things here. We have 2 points after the for loop, and it's indented. So the body of the loop is shifted to the right. Okay. So Shift Enter, it prints 10 times hello friends. Okay. But note something: the indexation starts from 0 and not from 1. So it's like C. Okay. Now, of course, you can start with 1 if you like. So just enough to put, if you want to start with 1, just type range of 1, comma 10, but it doesn't reach 10. It reaches 9. So if you like, if you want to print it 10 times starting from 1, you have to put range from 1 to 11. Okay, and it's possible that you have problems in typing this, because suppose that you forgot the 2 points, then you will get an error, okay, a syntax error. If the indentation is not correct, you will also get an error, okay? So pay attention to this. Okay, so this is our second line of code. Now, there's another way. Instead of doing a for loop, suppose you want to find all the integers, the square of the integers, the perfect squares for I between 0 and 3. What do you get? You can write this code. I squared, this is the symbol for exponentiation, double star. The star is for multiplication, double star is for exponentiation. Okay, and you put everything between brackets. And this will give you what? This will give you 0 squared, because you start from 0, 1 squared, 2 squared, and 3 squared. Don't reach 4. Okay, if you want to go to 4, you'll have to put 5. Okay, and now the while loop, it's like in other languages, but same remark: 2 points, and there is an indentation to the right. Okay, so pay attention to this. So this code here repeats, it's the same as here, but with the while loop. Okay, and plus or equal 1 is like C, so you can write I equal I plus 1. So you just replace I by I plus 1. So you increment at each step I by 1. I hope you are familiar with this. So we get exactly the same result. If you want to start with 1, you just type I equal 1, and depending on where do you want to, okay, so you can change the code if you like. I recommend actually that you take these, you type by yourself these codes, don't just copy it, and try to change the parameters and see what happens. So try to experiment and play with the code. It's very useful. This is how you learn, actually. Okay. Now, another way to do a for loop, if you have two, suppose, for example, you have a list of things. For example, here I have 3 adjectives: powerful, cool, readable. I put them in a list. Okay. And now, if I enumerate this list, what do I get? Okay, so this is the list. It doesn't print actually, but you can use this enumerate. So enumerate words. It's a list having 2 indices actually. What the index of the word and the word itself. So it's a kind of dictionary, if you like. And let's see what happens if we execute this loop. So at each step, so the index is 0, it starts from 0, so it's 0, 1, it's incremented by 1 each time, and the item actually is in the word. So the item is the word. Okay, so 0 powerful, 1 cool, 2 readable. Try to change it, for example. Try to put something like beautiful. Okay, what happens? We have to execute this first. And you see so try to experiment with these things. I took this example from the SciPy lecture. Okay. Maybe I need to L. I don't know. Maybe it's beautiful double L. I don't know. Okay, you check it. Now, okay, this is the basics of loops. Of course, there are other things, but in this quick introduction, I don't have time to cover everything. So, because it's an overview. Now, let us go back to functions. Functions also are defined. The syntax is the same as actually. So you use the keyword def, and it should be printed in bold green. Okay, so this is the keyword for a function. So now the Python compiler knows that you want to define a function. This function is called disk underscore area, and you put the argument here. So you can put radius, for example. So the area of the disk is pi r squared. Now of course here you can put any other variable. You can just put r. Okay, so and of course you have the 2 points here, and indentation to the right is very important. Otherwise you get errors. So if you execute this, okay, now there is a function called disk area which is stored in the Python memory. Okay, let us compute this function, for example, when the radius is 2. Okay, and we get, of course, pi times 4. Okay, try other, and of course, now in programming, it's a good thing to put words instead of variables because you can understand better what's happening. Of course, I can put t here if you like, but if I put t here, it's exactly the same function, but it's no longer clear what are we doing, what are we trying to do. I can write it in this way, t squared. Okay, but in this way of writing, it's exactly the same function actually. Okay, but so I encourage you to put to name your variables in a suggestive way. Okay, so let us try this area of 1. What we should get pi. Okay, 3.14. Okay, but I can also call this function anything I like. Okay, so this is your choice here, but of course the choice should be guided by simplicity and understandability of the code. Okay, you can put actually f, but if you put f here, okay, what is f doing? So what is the meaning of f? It's not clear. So if I put here f of 1 or f of 2, let us say, okay, same result. So now if you have a simple expression of the function, an algebraic expression like this one, px squared, we can use the lambda programming functionality. So I called it Joyce here, but you can call it anything you like. So Joyce here is just a function of x. So it takes x and produces 3.14x squared. Of course, you can put here t, but then you have to put t here. Okay. So Joyce now is the same as disk area, and Joseph 2 should be the same, should give the same result. Okay. So this is a convenient way if you have a simple expression like this to define functions. So you can use this syntax or this one. Okay. Okay. Now we have, as you know, in Python you have modules or libraries. We have the math module, which contains all the the main mathematical functions that you use every day, the elementary functions, and much more. So we have the logarithm. So let us import math. Actually, in Python, you have to tell the compiler precisely what to do. So it's unlike other languages like Matlab, when it loads everything. Here, it's a better practice to. So when you want to use something, you have to tell the compiler to load it into memory. Okay, because if you don't do it, the compiler will not recognize what is the log. Okay, so it's unlike Matlab, but it's good because you don't need to load something that you don't need in your work. Okay, so let us import math and try log2. And so this is the natural logarithm actually. Okay, log3, for example, log1 should be 0. Okay. So now actually the log is a function inside the math library, okay? But why do we do this? Why don't we just do log? Because there may be other libraries like numpy, which I'll see later, that contains also the function log. So now there are two functions actually. The log that comes in the math library and the log that comes from, for example, the sympy library or the numpy library or something else, okay? Now we have, of course, the usual cosine, but you have to put math.cosine. And pi, you have a constant in the math library called pi, so we have to put math.pi. Okay, now it may seem a little bit complicated, so this is just cosine of pi, which is -1. Now, it may be a little bit strange, but this is how Python works. If you want to have a more readable code, just can declare pi equal math.pi. And now, for example, let us do a vector having 3 components, 0 pi and 2 pi. Now this code is better. Let us see how a looks like. So it's a vector having 3 components. It's a list if you like. Okay, and okay, so now I want to introduce you to numpy, which is a very powerful library for mathematical computations. Everything you need to is there actually, all the functions, linear algebra, and everything you need. So usually, instead of typing numpy.py or numpy.log or numpy.cosine, we usually use a shortcut. So the syntax is import numpy as np. This is a standard practice in Python. So, and now when you do this, for example, you need to type the logarithm. Let us start with the logarithm. So I put here a. So np, let us say, .log now. This is the natural logarithm of 1, should give 0, exactly as before. Log2 should give as before. So now we have two functions actually, the log inside the numpy library and the log inside the math library, and they are not the same function. So now when you write this, Python now knows which logarithm you are using. Okay. So, and yeah. So let us try the exponential. The exponential of 0 is 1. The exponential of 1 should be around 2.7. So please try. So you can stop the video from time to time and try these codes on your own. Okay. And now, of course, I have the np.py because pi is a constant, not only in the math library but also in the numpy library. So we can use the same thing. And now And the numpy library is very good actually for working with matrices and vectors. So the basic construction is numpy.array. Okay, so it's a vector in a numpy format. So here, for example, I constructed a vector having 1, 2, 3, 4, 5 elements. So what is A? Yeah, so it's 0, pi over 2, pi, 3 pi over 2, and 2 pi. And we can define matrices, but we in numpy, but we so we program them we enter them line by line. Okay, so now A is a matrix whose first line is 4, 3, 5. Okay, but note the brackets are very important. Okay, so you may have errors in the beginning, so pay attention. So it's very sensitive. If you forgot one, let us say one bracket, you get an error. Okay, so it's only normal that you get errors in the beginning. So now A is a matrix 2 by 3. Of course, try to invent matrix 3 by 3 or 4 by 4 or anything you like. Okay, and in the numpy we can sort vectors or lists. For example, suppose that we want to rearrange the matrix in an increasing order, but along lines. So this is axis 1, this is axis 0. Okay, if I want to rearrange to order this matrix, we have along the columns, if you like, we can use the numpy.sort. Okay, let's see what happens. So we get 3, 4, 5, 1, 1, 2. So actually, it's what is it doing actually? It's arranging line by line. So it's arranged first the first line and then the second line. Okay, we can do the same thing if we like on the other axis. So we can arrange 4, 1, then 3, 2, then 1, 5. So we should get 1, 4, 2, 3, 1, 5. Let's see. Yeah, so 1, 4, because 1 is less than 4, and so on. Okay, so it's a different sorting of, yeah. If we just doesn't specify, if we don't specify the axis, we get what? We get, so by default the axis is 1, okay, not 0. Okay, let us continue our experimentation with arrays. Here I have a vector having 4 components. Okay, so it's -1, 2, -2, 3. Okay, very good. Now I have to break this into several parts. Okay, what is A less than 0? A less than 0 is a list actually. It's a Boolean array, if you like. So, so having actually 4 components. The first one is true because the first component is less than 0. The second component is bigger than 0, so it's false, and so on. Now, suppose, for example, you need to replace all negative components of an array by 0. Of course, you can do this by a for loop, but you can do this in a more elegant and more efficient way by using this syntax. So, okay, so we know now what is A less than 0. It's a logical array. Okay, and now, so yeah, I printed here actually, same thing, so I don't need that. Okay, and suppose now you want to replace all negative components of A by 0. So you just type A of A less than 0 equals 0. And let's see what happens. We should get what? We should get 0, 2, 0, 3, right? And this is precisely what we have. Okay, try to experiment with that. Suppose that you need to replace the positive by 0, or yeah, let us try, for example, A bigger than 0. What happens? We should get -1, 0, -2, 0, right? No, yeah, because actually so I have to repeat this process because I had 2 zeros before. So let us try A positive. Now it's false, true, false, true. And now I get minus, so I replace now the positive entries by 0. Okay. Okay, so this is a useful technique for modifying arrays. And of course, now the numpy functions, mathematical functions, work over numbers as well as over arrays. So for example, if I have, suppose that we have the vector 0 pi over 2 pi, 3 pi over 2, 2 pi. What is the cosine of this vector? Is the cosine of each component. Okay, so the 1 actually is the cosine of 0. This very small, actually, this is something around 0 actually, because it's the cosine of pi over 2, and so on. Then we get -1 because cosine of pi, and so on. Okay. Of course, we don't get exactly 0 because these are approximations. Okay, but it's a very, very small number. So we can take functions. We can apply the usual mathematical functions not only to scalars but only to vectors, but also to vectors, and this is very important in plotting. Okay, so now I move to the important part about basic plots. Now, so Python has plotting libraries, one of them being Matplotlib. But instead, once again, of writing every time matplotlib.pyplot blah blah blah, we do a shortcut, so as we did for numpy, and instead of all this this big expression, write plt. So now this is, and plt now, so we has a function called plot. So this is actually it's used by all Pythonistas around the world. So you don't need to worry much about all these details, but how does plot works? Actually, it's like other softwares. Actually, it plots a vector against a vector. So let us start with a simple example. Suppose I have the vector 0, 1, 2, 3, and the vector of squares 0, 1, 4, 9. So it's just a parabola, but just we took 4 points. So what happens if you plot x against t? We should get something like a parabola. Yeah, because I have to put Matplotlib online, I think. Yeah, sorry, I did a mistake. So if you want to see the plot, you have to type this command or something equivalent, Matplotlib online. Otherwise, it doesn't display. So let us comment about this very simplistic figure. So we have 4 points on the x-axis and 4 points on the y-axis. We have 0, 0, 1, 1, 2, 4, and 3, 9. So 4 points, 1, 2, 3, 4. And when we plot, actually, so Matplotlib plots these points and connects them by lines. Now, of course, it's not a good way to plot a parabola. If we want something better, we have to take more points. Okay, so if we, for example, take 1.5 here, and here we put 1.5 squared. Okay, we should get better. We should get a better figure. Shift enter. It's becoming smoother actually. Okay, so the more points you take, the smoother the figure gets. But 4 points is very little for a good graph. What we can do is actually, for example, suppose we want to plot the cosine now. Okay, 3 or 4 points will get an unsmooth curve. So we usually take 100 point or something bigger. So one way of doing this is to take a long vector having, let us say, 100 entries. So we divide the interval 0 to pi into 100 equal parts. Okay, so this is the t. Okay, and then you take the cosine of this vector, and then you plot them against each other, and you should get something very smooth, like this. Okay. Now try to take another function if you like, sine, or try to experiment with a bigger range. For example, 0, 4 pi to see the repetition, for example. Let's try 0, 4 pi. Okay, so get, if we take, for example, 10 points, you get something actually very coarse. Yeah, it's still. So you see that this controls the accuracy. So 100 is good usually. Okay, you can take more. And of course, there are so many parameters in plot. You can control the color, you can annotate, you can do a legend, you can do so many things actually, but this is the most basic plot, just plotting a vector against a vector. Okay, here let us try something more. Let us try to plot a parametric curve given by cosine cube sine cube. Okay, so here I took t between 0 and 2 pi, and I divide into 100 equal parts. Then I took the vector cosine cube, the vector y cube. Actually, yeah, I did it here. It's not online. It should be inline, not online. Yeah. So here I'm plotting x. So it's a parametric curve, and this should give you what? Should give you this loop. Should get this loop. But note that it's the scale on the x-axis is not exactly the same. If you want an orthonormal system, you should precise that the axes are equal. Okay. Okay. So now if you take the same scale, you should get something like this. Okay. Try to experiment with other curves, with other parametric curves, and try to change the color if you like. Okay. And this is another example where we add, for example, a noise to the cosine. Okay, so here we take, we divide 0 to pi into 20 equal parts, and y is just cosine plus a random noise, so it's random.rand. Okay, and then we try. So what happens actually if you try? I took this actually from the SciPy lectures. Okay, so if you try to break down this code into smaller entities. So first, what do? We take 20 points actually, which are perturbations of the cosine. Okay, and now we try to fit two things. We try to fit a polynomial of order 3, and we fit the cosine actually, and this is what we get. So the first fitting actually is in orange, right? And the cosine actually is in red. Okay. So you see that these two are approximations of these. So we are trying to, this is what we call a fitting curve. And it's very important because in practice, this is, you have a data set and you try to fit a mathematical function in it. Okay. So which one fits better actually? The cosine, of course, fits better because this is an artificial data set actually, because it's a cosine. So the cosine fits better than a third order. Try to fit a fourth order polynomial. See what happens. Yeah, it's better now. Okay, because okay. So it's the same thing, but actually it's okay. I hope you understood this. Try to experiment with this code. Okay. Now, as I said, you can annotate your code. You can change the colors, the line width, the line style. You can put labels. You can put a legend. This example, I took it from the SciPy lectures. Okay, so I suggest that, so you get something like this. You get cosine sine with a legend, with two different curves, different colors, and then annotation. So it's very interesting actually. I will don't have time to comment everything now, but if you want to really learn that, take this code and play with it, experiment with it, do it for other functions, okay? So you just need some time to get familiar. So, because I just wanted to give you some possibilities, some graphical possibilities of Python. And the next result, actually, also I took it from, you can color regions like this, okay, with plt.fill, okay, if you like. It's different colors. So we will not need all these features in this course, but this is just to give you a taste of what Python is capable to do, of doing. And of course, you can plot three-dimensional figures. Like, for example, here we have, if you want to plot the cosine of radical x squared plus y squared, then you have to use another library, not the Matplotlib the Matplotlib. Okay, so it's MPL toolkits.mpplot3d. Okay, so it's just so in three-dimensional plotting, it's approximately the same. So you have, but instead of having a vector against a vector, you have a grid, a mesh grid against another mesh grid, another vector actually, or another mesh grid. So you apply actually the function to each point in the grid, and then you get a surface. Okay, so it's just a syntax. So try to experiment with it. Try other functions. See what happens. Here we have the cosine of this, but you can take the sine. You can take other things. Okay. And finally, to conclude this section, we can also plot vector fields. Okay, it's okay, by using the quiver plot.plt.quiver. Okay, so you have to press here. It's the vector field whose components are minus y and x. So it's just a rotating field. Okay, try other fields if you like. There are so many parameters like the line width, the color, and so on. Okay, so try this. So this concludes the first part about basics, Python basics. Now I want to introduce some linear algebra. Okay, let us start with the matrix. Actually, it's a stochastic matrix because, so we shall encounter it later. It's just a 2x2 matrix of positive elements, and the sum of each line is 1. So this is what we call a stochastic matrix. Okay. Now we have two notions of multiplications for matrices. We have the element by element multiplication and the usual matrix multiplication, and these two do not coincide. For example, suppose that you want to raise each element here to the power 2. Then you should get what? You get this is squared, 0,2 squared, it gives you 0,04, 0,8 squared, and so on. And don't confuse this with a multiplied by itself. As okay, for this operation, you need to use a sub-library of the numpy library called linear algebra. And linear algebra contains a function called matrix power, matrix underscore power. Okay, and now a squared, so a times itself, should give you something like this. So don't confuse these two. And now let us see what happens if we take a3, a4, a5. What happens as n tends to infinity? So we just did an experiment. We took n from 2 to 20 and computed the successive powers. So a2, a3, a4, a20. Let's see what happens. When n equal 2, we get this matrix. It's still stochastic, so the sum of each line is 1. N equal 3, we get something else. N equal 4, n equal 5, etc., etc., etc. What's happening ultimately, actually? So already we are seeing something, a convergence here. 0.27, 0.72, 27.72. So it seems that actually this AN converges to some matrix with identical lines, with identical rows. And this is, we can prove that actually mathematically, but this is a test of this theory that AN as n tends to infinity converges to a stochastic matrix with identical rows. It's a very particular case of the ergodic theorem that we shall encounter later. Okay. Now, what can we do with? We can compute the determinant. For example, let us consider another matrix. Here I use SciPy, but same thing actually. I don't need. So SciPy actually is another library built on top of numpy. Okay. So actually, I don't need the SciPy. Just numpy is enough. So np.linearalgebra.determinant. So this is the matrix 1, 2, 3, 4. And the determinant is around minus 2y, because this is 1 times 4 minus 2 times 3, which is minus 2. Okay. We can, okay, so the matrix is invertible, and let us, okay, put here np.linal. So we can invert A if it's invertible. So I have this inverse here. And we can multiply B by A. Okay, of course, we can use the matrix. So one easy way to multiply B by A is the function B dot A. And you should get something close to the identity, 1, 1, 0, 0. But it's not exactly the identity because of numerical errors. Okay, but it's very close to the identity because B is the inverse of A. We can also find the eigenvalues of A. I think there's a problem here. I think this feature is, yeah, I'll delete that. Okay. Yeah, okay, so sorry, I did an error. So the function linalg.eig gives as output the eigenvalues and the eigenvectors. So usually what we do is we store the eigenvalues in an array called eigenvalues. We can call it everything. We can call it A if you like. So let us call it A. And the eigenvector B, because we have two outputs. So we compute the eigenvalues and eigenvectors of the matrix A. Okay, and now what is A? We should get what? We should get two eigenvalues. One is negative, one is positive. And the eigenvectors are given by actually a matrix whose columns are the eigenvectors. So we have two eigenvectors. First one is minus 0.805. The second one is minus 0.4, minus 0.9. Try to check this on other matrices. Okay. And now, also I took this next example from the SciPy lectures. This is just a formula for approximating pi, but it's not the best formula. Just I wanted to test it. And as I told you, in many cases we can avoid writing loops because loops take more times than the built-in function. Like for example here, the function .np.prod does what actually? It computes the product of all elements in some vector. Okay, so you put this 4k squared over 4k squared minus 1, and we compute it from k from 1 to, let us say, 1000, and you do the product. So this is more efficient actually than just writing a loop. Of course we can do a loop, but it's more efficient, and we get this approximation of pi, which is not bad, but it's slow actually. A better approximation is given by this constant, so by pi. Okay. So this just to illustrate that vectorization is better than loops. Now try to do a for loop and test to see which one takes longer. and which one is better. Okay, now we move to some numerical computations. Polynomials can be defined as list. Okay, so because the polynomial is determined by its coefficients, we're starting from the highest degree. So 3 to minus 1, 3x squared plus 2x minus 1. So this is one way of defining polynomials. So the function is poly 1D. So what is p of 0? It should be minus 1. We can access the order. We can compute the order of the polynomial. It should be 2. And we can compute even the roots. Okay, because computing the roots of polynomials is something very standard in numerical analysis. So we have 2 roots here. We may have complex roots. Let's try to take another polynomial. For example, let us take x4 plus, let us take x2 plus 1. So it's 1, 0, 1. Okay, so it's the polynomial x squared plus 1. And at 0 it's 1. The order is 2. The roots should be what actually? I and minus I. Yeah, they are called j here. Okay. So there are 2 roots, the 2 imaginary, I and minus I, or j and minus j. Okay, we can also compute integrals by quadratures, that you learned in second year. We have Simpson rules and so on. So, okay, here I use sympy. I don't know why, but of course it exists in numpy. So this is an approximation of the integral from 0 to pi of sine x. So sympy is a library built upon numpy. Okay, and it has a function called integrate. So it gives you the result with the error. So if you do this, we get the result. So the result is 2, and the error is very, very small, 2 to the times 10 to the power minus 14. Okay. Okay, try to find the numpy analog. Okay. And finally, I will end with some symbolic computations with the sympy module. Okay, so we have to import it as usual, but instead of writing sympy every time, you just write sim. So we import it as sim. And now we can compute exactly with rational numbers rather than just approximation. So for example, A here is the rational number 1/2, okay, and B is the rational number 1/3. If I add them, I should get what? 5/6. Okay, so try to do with other examples. Now we can define symbolic symbols actually by using this syntax. So x is the symbol x, y is the symbol y, and let us, for example, try to expand x plus y cubed. And we get as expected x cubed plus 3x squared times y plus 3xy squared plus y cubed. Okay, let us try to expand the cosine x plus y. It's minus sine x sine y plus cosine x cosine y, as we expect. We can simplify fractions. X plus xy over x should give you what? A y plus 1. Okay, let us simplify cosine over sine. It's 1 over tangent. We can compute limits, okay, with this syntax, sim.limit. For example, sine x over x. So we put with respect to x as x tends to 0. Okay, should get 1. Let us try something else. For example, let us try what happens at pi actually. Yeah, it should be 0. Okay, but here actually it computed it numerically, not symbolically. Okay, so what is the limit of sine square x over x? It should give us 0, right? Ln x over x as x tends to 0. Here as x, yeah. Actually, no, this is plus infinity actually. Let me try this to infinity. Yeah. Okay, so right? Okay, we can do both actually. If you want ln x over x at infinity, it should give us what? It's 0. But if we want to compute it as at 0, then we should get what actually? Ln x over x at 0 is minus infinity actually. Okay, this is the symbol for minus infinity. Try to experiment with our function. Now we can differentiate by using sim.diff. The derivative of sine x is cosine x. The derivative of sine 2x is minus 4 sine 2x. This is the second order derivative. Okay. The first order derivative is 2 cosine 2x. Second order derivative minus 4. Third order derivative, etc. So you can play as much as you like. We can compute the Taylor series of cosine. We can find the antiderivative of some functions. The integral of sine is minus cosine. The integral of x squared between 0 and 1 is exactly 1/3. It's an exact computation. And so on. You have so many examples actually. These are definite integrals. From 0 to infinity of e minus x should get what actually? You should get 1. Yes. And here we should get what? We should get e minus x squared, should get radical pi. From minus infinity to infinity. Yeah, so you get square root of pi. Okay, we can solve equations. We said that with solve set. We get 4 roots here, minus 1, 1, minus II. Okay. What if we solve the equation x plus 1 equals 0? This has actually infinitely many complex roots. So everything, it's a set actually. It's pi plus 2n pi times I times the, okay, and n varies in the integers. We can solve linear systems very easily. Okay, we can factor polynomials if you like. Okay. Now, what did I do here? Yeah, we can solve differential equations. So here we are solving the differential equation. Let us try to solve the differential equation f double prime plus f equals 0. Should get a cosine plus b sine, right? But this are not numerical solutions. These are symbolic solutions. Okay. Next equation, f double prime minus f. This is less trivial. F prime plus x f of x equals 0, which means that f prime equals minus x f of x. So if I separate the variables, I divide by f and integrate, I should get what? I should get an exponential. So it's a constant, it's an arbitrary constant, times the exponential of minus x squared over 2. And finally, the last example, just to impress you with some graphics. This is the famous Mandelbrot set, which is the typical example of a fractal set. We can easily plot it with Python, with Matplotlib. So I took this code from the SciPy lectures, and look what we have. Very beautiful. Yeah, we have this very beautiful Mandelbrot set. I will ask you to, if you like this picture, to do a small research about the Mandelbrot set. How is it defined actually? It's a set of complex numbers. And the code is not difficult. Okay, you can try to break it down, but it's a little bit advanced because there are many features here. But so this is a little bit advanced, but just to illustrate the graphical capabilities of Python, of this beautiful language. Now, we will not need everything I covered today, because this is just an overview. And I told you that there are so many great courses on Python online. Take the one you like, and you can, okay? So next time we'll start implementing the Monte Carlo, the linear congruential random generator. Okay, so thank you for your attention.